Greetings and welcome. In this video session, we are going to study construction and working and analysis of two-stage compression system with flash gas removal method. Now, in our introduction session, we had discussed that why the multi-pressure system is required and why single stage system is not fulfilling the requirement of low temperature, because especially multi-pressure system is used where the temperature requirement is very low. So where the temperature requirement is below minus 30 degrees Celsius, 40 degrees Celsius, in such cases evaporator temperature is very at a low level, and in that case here this evaporator line, this line is falling down. And again, to reach to that level, compressor has to work more, and also because of that compressor exit point goes upper side. So that is why here, if you see here, this is a dashed line, 2 dash is a compressor exit. So when the single stage system is used for the such application, in that cases this condenser pressure is increasing, and when this condenser pressure is increasing, then this dash line 2 dash 3 dash is going up, and subsequently it reduces the cooling effect, because this 3 dash 4 dash, this is a flashing in the expansion process which occurs. This flashing effect is more than the regular 3-4, that is a single stage capillary action or single stage 3-4 expansion process. So that is why here this flashing we have to reduce. So for that purpose, this flash gas which is developed, that is to be removed, and that is why there is a one of the method, that is a flash gas removal method. So this method we use in the flash gas removal method multi-pressure system. And also there is another concept that here two compressor, more than one compressors are used in a multi-pressure system. So that is why we will see now. So here is a condenser. From the condenser, the liquid which is coming out, this liquid in a regular system is given to the evaporator, the single stage system. But here in the flash gas removal method, what is done, so here one device that is called as flash chamber, this is introduced. So flash chamber, what does? Flash chamber separate the refrigerant into two parts. It sends the liquid refrigerant to the evaporator, and it removes the vapor which is developed during the flashing process in an expansion. So that vapor is removed and that is sent to the compressor. So here this connection from the condenser, means this liquid line connection, this is given to the flash chamber first of all. So that is given through this wall. So here expansion wall is given. Thus this liquid is passing to this flash chamber. Now during this expansion process, whatever flash gas is removed, flash gas is developed, that flash gas is removed and that is taken out, and the liquid part, that is given to the evaporator. So here if you see in the diagram, pH diagram, here we can find this process like this. So this is a 1 to 2 compression. So here will be after the evaporator point number 1, then here will be first compressor C1 to this first compressor, this input is given 1 to 2, that compression is taking place in a low pressure compressor. This is called as low pressure compressor. From the low pressure compressor, the vapor is coming out. This vapor and the vapor which is coming out from the flash chamber, these both vapors are mixed together, and these vapors are given to the next compressor, that is high pressure compressor, compressor 2. And from this compressor, then this connection is given to the condenser. So here will be like this. Now here the point number 3, that is a point number 3 which is coming out of the flash chamber. This will be saturated condition. Here this vapor which is coming out of the first compressor, this will be superheated vapor. So this superheated vapor and this saturated vapor, two and three, will be mixed, and then these will go to the compressor. So here condition of this vapor which is passing to the next compressor, that condition will come between the point number 2 and 3 here. So then 4 to 5, this will be high pressure compression. 4 to 5. Then 5 to 6 will be condensation. 6 to 7 will be expansion here after the condenser. And then at this point 7, here inside the flash chamber, I already mentioned that here this flash chamber is separating the vapor. So vapor part will go on the right side and liquid part will go on the left side. So liquid part means this point. So this point will be what? Point number 8. So here after this is point number 8. Here we need to introduce one more expansion valve. So here after the expansion valve, here this expansion which is taking place, that is 8 to 9. Means from the flash chamber, liquid which is coming out, that is coming out to the expansion valve, this expansion valve which is at the low pressure envelope. We call this total envelope as a low pressure envelope, and this upper envelope we call as a high pressure envelope. So in low pressure envelope, here is the expansion valve. That expansion valve do the process 8 to 9, and then this 9 point which is here onward, that this liquid goes to the evaporator. So here evaporation process occurs. So in this way, use of flash chamber is done in the case of multi-pressure system, and that is why this system is called as flash gas removal method. Multi-pressure, or now this is what, two-stage compression. So that is why the name of the system is two-stage compression system with flash gas removal method. Now we can see the analysis part of the system. So already that diagram, construction diagram, that already we studied. Now in this, now we will use the next concept, that is what, mass flow rate. Now here are the two mass flow rates required. Here if you see, this is the envelope, lower envelope, as I mentioned. So through this lower envelope, mass flow rate which is passing, that is m1 dot, this mass flow rate is passing through this evaporator and it is passing through this compressor. So 1 to 2, this is a mass flow rate which is passing through the compressor number 1. And here from the flash chamber, the mass flow rate which is coming out, that is a vapor removal. Vapor removal, that is why it is m2 dot minus m1 dot. So this vapor is mixing with this m1 dot. So finally m2 dot minus m1 plus m1 means minus plus get cancelled, and here in the upper envelope means through the compressor 2, that is high pressure compressor, here the mass flow rate which is moving, that is a m2 dot. So here we can show on the pH diagram, m1 dot is moving through the lower part and m2 dot is moving through the upper part. Now this we will use to write the formula for the compressor work done 1 and compressor work done 2. So for that, now we will see here the next slide. So m1 dot we have written here, that is a mass flow rate through the low pressure compressor C1. m2 dot is a mass flow rate through the high pressure compressor C2. Unit of it is a kg per second. Now to write the formula for compressor work, the formula is what? W dot 1 is a work done for the compressor 1 will be equal to respective mass flow rate for the compressor 1 m1 dot and the enthalpy difference across the compressor 1. So here if you see across the compressor 1 pressure enthalpy difference, you can see here in this diagram, PA diagram. So that is what H2 enthalpy is exit of the compressor, H1 is a entry enthalpy of the compressor 1. So H2 minus H1 multiplied by this mass flow rate m1 dot, that is what the work done of the compressor 1. Similarly for compressor 2, mass flow rate will be m2 dot and respective enthalpy difference H5 minus H4. In the diagram if you see, this is the 4-5 process. Here in the schematic diagram if you see, this is the point number 4, entry to the high pressure compressor 2, exit means discharge point is a 5. So 4, 5. So enthalpy difference will be 5 minus 4. So here in this diagram, in this formula, W dot 2, that is a work done for the compressor 2. Both work done will be in a kilowatt. Net work means total power which is required to drive or to run the system, that is what summation of these two works will be in kilowatt. This was about the compressor power. Now refrigerant effect. So for that again refrigerant effect, where we get refrigerant effect we get at the evaporator across the point number 9 and 1. So here if you see, this is a 9 enthalpy H9, 1 point that is enthalpy H1. So H1 minus H9, that is the amount of heat absorbed by the cooling coil from the space which is present over there. From the space, the amount of heat that is absorbed by the evaporator. In turn, cooling effect is developed in the evaporator space. So this cooling effect will be equal to what? Respective mass flow rate multiplied by enthalpy difference across the evaporator. So mass flow rate is what? M1 dot, and enthalpy difference will be what? H1 minus H9. So that is why here if you see the formula for the cooling effect, now here notation we use for the cooling effect, that is Q dot L. Q dot, that is heat transfer rate, L means load, cooling load. So Q dot L is equal to mass flow rate M1 dot multiplied by H1 minus H9, bracket complete. This will be also in kilowatt. This is the output, and compressor power is the input. So ratio output to input, that is called as COP, means coefficient of performance, is equal to what? Q dot L divided by total power. So in the numerical you can solve this by using this formula and you can find the COP. Now, in this case, in the whole journey, if you see from the diagram, we obtain, means from the chart, we obtain the enthalpies which are on the saturated line. Means on the saturated line, points which are here, point number 1, point number 3, point number 6, 8. These 4 points are located on the saturated line. So directly of these points enthalpies we can get when these points we will drop on the enthalpy scale. So H1, H3, S6 and S7. Now 6, 7 is isenthalpic process because this is the expansion process. That is why S6 and S7 will be same. Similarly 8 and 9, this is also isenthalpic process, constant enthalpy process which occurs in a lower part. H8 and H9 will be identical. So that is why here from the chart, whatever enthalpies are obtained directly, these are written here: H1, H2, H3, H5, S6, S7, H8, H9. These all enthalpies are obtained because point number 2 we can get by drawing the line parallel to the isentropic line. In the chart what we use, there are different isentropic lines. So we take reference of these isentropic lines on the chart and we draw a line or curve which is parallel to the isentropic line through point number 1. This line will be cutting or intersecting with this intermediate pressure line. Here we get point number 2. Similarly, here point number 5 we obtain, but for that this point number 4 is to be calculated. This point is already we said that it is a mixing point of 2 lines. So we don't know currently where exactly point number 4. So for that calculation, to find H4 we have to use now formula. So for that now we will take help of the energy balance equation. Energy balance means what? Amount of heat entering to the system and amount of heat coming out of the system. Now here we will take system means what? This portion, compressor 2. So compressor 2, there is a entry, point number 4. Point number 4. And here this 2 and 3, these 2 lines are mixing together. So here if you see, here you can get mixing of these 2 lines, M1 dot into H2. M1 is a mass flow rate of this line, H2 is the enthalpy of point number 2. So product of these 2, that will be heat content which is present in the refrigerant, vapor refrigerant, which is coming from the compressor 1. Similarly, heat content which is present in the line which is coming from the flash chamber will be what? This corresponding mass flow rate M2 dot minus M1 dot, this bracket, multiplied by point number 3 enthalpy. So here M2 dot minus M1 dot bracket complete enthalpy S3. This will be heat content present in the line which is coming from the flash gas chamber. These 2 lines are coming together, means there is a summation of these 2 heat contents, and these are going to the compressor. So at the compressor entry, condition of the refrigerant will be what? Point number 4. So that is why on the right side here, total heat of these 2 heat content at the compressor entry will be what? Point number 4 enthalpy H4, and mass flow rate which is passing through the compressor 2, that is M2 dot. So M2 dot into H4. So we get this equation. This equation is called as heat balance equation or energy balance equation that we use. Now in this case, M1 dot we find by the formula here. This already we discussed. This is a cooling effect at the evaporator formula. This cooling effect is a capacity of the system that is given in the numerical in a TR. So this M1 dot, we can write the formula for M1 dot by arranging this equation. How? M1 dot is equal to Q dot L divided by H1 minus H9. But Q dot L is given in a TR. So here TR to kilowatt conversion. That is why we multiply this TR value with 3.517. So here we get M1 dot. Now this M1 dot we use here. Enthalpy H2 we obtained from this chart. Enthalpy S3 also we obtained from the chart. So here unknown is what? H4. So by putting the value of H4, by putting the value of mass flow rate 2, mass flow rate is unknown. When we put the mass flow rate here, then we can get the enthalpy of H4. Currently here are two unknowns. So to find M2 dot, we have to again use method, that is the energy balance method. So to find M2 dot, here we use energy balance equation at the flash chamber. So here this flash chamber, if you see, this flash chamber will have three lines. This line which is coming out from the flash chamber, liquid line. This line which is coming out, that is a vapor line which is going to the compressor. And this is a line which is entering to the flash chamber, that is a liquid line. Means to this flash chamber there is a one liquid line in and two vapor lines out. So we can write the equation total heat entering is equal to total heat leaving. Total heat entering here, if you see, then you can get the formula M2 dot into S7, because here mass flow rate which is coming out from the condenser means through the upper envelope M2 dot, this mass flow rate is going to the flash chamber M2 dot. Respective enthalpy will be what? Point number 7. This is point number 7, because this is point number 7 that is coming from the expansion process 6 to 7. So here 6 to 7 is a expansion process. So this enthalpy. So that is why here this is a heat content M2 dot into S7. This is a entering heat equal to heat content which is coming out of the chamber. That out of that first is what? M2 dot minus M1 dot, this mass flow rate, multiplied by this heat value, that is the enthalpy value, point number 3, H3. And another heat content which is leaving this flash chamber, that is what? Point number 8, enthalpy H8. And this mass flow rate is going to the evaporator and further to the compressor 1, that is what? M1 dot. So M1 dot into H8. So here we can use this energy balance equation. In this equation we put the enthalpy, we put the value of M1 dot, and then we find the value of M2 dot, mass flow rate of the compressor 2. This mass flow rate we use here in this equation, and then we can get enthalpy of H4. So in this way we have seen in this video session that how to use flash chamber to remove the flash gas which is developed during the expansion process in order to increase the performance of the system or to overcome the limitation of single stage refrigeration system. Also we have seen schematic of the flash gas removal method, pH diagram, in that all the points, then after that all the enthalpies, how to obtain. After that we have seen energy balance equations, and then finally output, that is a cooling effect, input, that is a compressor work in a both low pressure, high pressure, net power to required to run the system, and finally coefficient of performance, that is ratio of both. So in this way we have seen complete theoretical part of the two-stage compression system with the flash gas removal method.